Hello, this is Mr. Best. Welcome to Chapter 8, Polygons and Circles, Lesson 8.2.1. Start with question 71. Examine the shape at the right. Find the area and the perimeter of the shape. So we see that we can have it's written on a coordinate plane, so we can kind of count what each of these links are. So we have 5 here, 2, 4 here on the bottom, 4 on the side, 3, 2. And the only one we don't have is the diagonal, but we can figure it out because we can create a right triangle. It looks like this right triangle would be 4 and 4, which is an isosceles, and that means we have 45, 45, 90. So this hypotenuse, if we want to use our special right triangles, would be 4 square roots of 2. And so now we can go ahead and find the perimeter, which is part A. So we'll just take all those side lengths and add them up. We start with the left 2 and then go to clockwise. 2 plus 5 plus 2 plus 3 plus 4 plus 4 plus 4 square roots of 2. And so that will give us 20 plus 4 square roots of 2. And that would be the exact answer. And then let's plug that in the calculator and see what we approximately get. So approximately 25.7 units. We're also looking for the area on this one. So we can break this up into different parts, and I'm sure there's lots of different ways we can look at this. So I'm going to go with, let's see, I'm going to create, I think, a rectangle and a trapezoid. So the rectangle I can see is 5 times 2, which is 10, so that's pretty easy on that one. The trapezoid, I'm going to have to do a little bit of work here. Not much, though. I think we'll be all right. So the trapezoid would be 1/2, and then the height, which we have, is 4, and then the sum of the bases. So that'd be 4 plus, and then on the top there, that's going to be a total of 8. So that would be 1/2 times 4 times 12, which would be 24. So the area is 24 units squared. Of course, plus my 10 units that I need to add on there. So found the area of the trapezoid, but then forgot the area of the rectangle. So it's actually 34 units squared. So that's part A. So let's look at part B. On graph paper, enlarge the figure so that the linear scale factor is 3. Find the area and the perimeter of the new shape. So I don't have the graph paper on here for this, but go ahead and enlarge it. Remember, the linear scale factor is 3, so each of the side lengths would be 3 times whatever they are right now. So for example, the 5 on top would become 15, the 2 would become a 6, and so on. So you can create that on graph paper. I'm going to go ahead and go straight to the perimeter and the area. The perimeter, as we might remember, is the linear scale factor is 3, so we just take 3 times the former perimeter, which was of the original 25.7 approximately. So if we times that by 3, our new perimeter will approximately be 77.1 units. And then the area, with our linear scale factor of 3, so r is equal to 3, so r squared is going to be equal to 9, and that will help us find the area. That means the area is going to be 9 times what it was of the original. So the area of the original was 34, so we take that times 9, and we will get 306. Let me try to write that again here. 306 units squared. And so once again, I didn't create the enlarged figure, but you can do that. I just found the perimeter and the area using our linear scale factor, and also knowing that the area is the linear scale factor squared, or r squared. On to part C. What is the ratio of the perimeters of both shapes, and then what is the ratio of the areas? Well, hopefully, if did this all right, is that the perimeter ratio should be the linear scale factor, which is 3, and that's how we created it anyway. So 77.1 divided by 25.7. Now, if you actually went and redrew it and recalculated everything, it'll still be, in terms of that scale factor, will still be 3, or that ratio will still be 3. So this is 3 over 1, or 3 for the perimeter. And I shouldn't put perimeter is equal to, it's the ratio of the perimeter. And then for the ratio of the areas, let's go ahead and make sure I write this. So this is the ratio of the perimeters. And then we'll do a ratio of the area, and that will be 306 divided by 34, and that will give us 9. So once again, that ratio should be equal to R, and then the area ratio should be equal to R squared. Question 72. Sandeep noticed that when he looked into a mirror that was lying on the ground 8 feet from him, he could see a clock on the wall. If Sandeep's eyes are 64 inches off the ground, and if the mirror is 10 feet from the wall, how high above the floor is the clock? Include a diagram in your solution. Alright, let's see if we can get a diagram, see what this is going to look like. So, looking at a mirror 8 feet from him, so let's put him right here. Here's the mirror, that's 8 feet away, and then he could see a clock on the wall. So let's put the wall over here. If his eyes are 64 inches off the ground, so if his eyes are up here, this would be 64 inches. And if the mirror is 10 feet from the wall, so now we can go to here, that's 10 feet. How high above the floor is the clock? And so then the clock's somewhere on the wall. Alright, so double check all that. I think I got that set up correctly. We're trying to figure out how high above the floor is the clock. So we're looking for this distance here. Alright, I went ahead and marked. I noticed that our units was in inches and feet. So I went ahead and changed 8 feet and 10 feet to inches so that I had everything in the same units. Let's go once again. I think I erased on accident. From here to here. And so my clock and stuff might not match up. But what we're looking at here is we have a right angle on the wall and with Sandeep. We also have that these two angles right here are going to be congruent based on reflection. So by angle-angle similarity, we know that the triangles are similar to each other, so we can create a ratio. And what we're looking for, once again, is we're looking for, this height over here. Might not look exactly with where I placed the clock, but that's fine. And so let's see what we have here. We can create ratios with similar figures. So let's go, we're going to go with the triangle on the left. So we'll start with the 96 inches over the corresponding part on that one, which would be 120 inches in terms of the side length. And that should be equal to, we have the 64 inches to Sandeep's eyes, and then the h value, which is actually what we're trying to find, the height from the floor to the clock. So let's go ahead and multiply this and see what we get. So that is 7,680, and we're going to divide that by 96 and see what we get. We get a value of 80. So let's see. How high above the floor is the clock? The clock is 80 inches above the floor. And so looking at similar figures, we were able to calculate what that height was. Question 73. Mr. Singer has a dining table in the shape of a regular hexagon. While he loves this design, he has trouble finding tablecloths to cover it. He has decided to make his own tablecloth. In order for his tablecloth to drape over each edge, he will add a rectangular piece along each side of the regular hexagon as shown in the diagrams below. Using the dimensions given in the diagram, find the total area of the cloth Mr. Singer will need. Alright, so let's go ahead and start. We need to find the area of the hexagon, probably. So let's go ahead and see what we have here. So across the vertices here is 6 feet. So if we draw in the rest of them just to kind of get an idea here of what's going on, we create our 6 triangles, and that means that each of these lengths here would be 3 feet. So if we look at one specific triangle, I'm just going to make it a little bit larger so I can try to draw things in a little bit careful. So then we draw this is 3, this is 3, and we'll put in the height here so that we can find it if we need it. And if I try to find the angle up top here, remember that's 360, and 6 triangles divided by 60, or 360 divided by 6 would give us 60. So this angle itself is 60, but then if I, like I said, if I split it down the middle, then each of these angles right here would be 30. So we're looking at each of these triangles represent an equilateral triangle. And so to find the area, I can split it up and get 2 smaller triangles, 30, 60, 90. And that will help me find the additional information. So for example, I have the hypotenuse. So this length, since it is equilateral, they're all the same, but that would be half the hypotenuse the short leg is, which is 1.5, and then the long leg is the square root of 3 times that, so we get 1.5 times the square root of 3. So the area of that triangle is 1/2 times the base, which is 3, so this whole thing down here is 3, and then the height is 1.5 times the square root of 3. Now there are 6 of those, so let's just go ahead and figure out what one of them are, and then we'll multiply it by 6 to find the area of the hexagon. So the area of one of the equilateral triangles is 3.897. I'm just going to keep it keeps going, but I'm going to keep that number in the calculator, and I'm going to go ahead and multiply it by 6 total triangles. So therefore the area of the hexagon is equal to approximately, I guess I should say, 23.4 feet squared. So that will be the area of the hexagon. Now we have to add, in addition to those, these tablecloth pieces. So you can see it's 1 foot. So if I take that off of kind of here just to show you the triangle, we know this is 3. Because that was the length of the base of the triangle, and then we know this is 1. So each of these additional rectangles are going to be an area of 3. So you have 1, 2, 3, 4, 5, 6 again. 6 times 3 is 18. So that gives you an additional 18 square feet in the tablecloth. And so once you add that in, you get a total area of the tablecloth to be approximately 41.4 feet squared. Question 74. What is the probability that x squared plus 7x plus k is factorable if k is between 0 and 20, including both of them, and k is an integer? Alright, what is the probability that x squared plus 7x plus k is factorable if k is between 0 and 20 and k is an integer? Alright, so I would be interested in how some of you guys think about this one. My kind of initial thought is to start kind of working backwards the way we normally do. We create our generic rectangle. We know that's an x squared. We use our diamond to answer the question that we know that our numbers have to add to give us 7x, and usually they would multiply to give us this k value. So that would be kx squared, I guess. And so this is kind of what we start with. Now we're looking at all of these numbers between 0 and 20, which is 21 total numbers. So I guess I'm thinking we just kind of go through and check all 21 of them. If there's another way that some of you guys are thinking about it, I'd be interested in hearing how you did that. So if I say, for example, if this number is 0x squared, what multiplies to give you 0x squared but adds to give you 7x? Well, that would be 0x and 7x. It adds to give us 7x. It multiplies to give us 0x squared. So that would work. So 0, if k is equal to 0, that works. And then we just kind of, I guess, repeat and see what we get. So what happens when it's 1x squared? Can we multiply to give us 1 and add to give us 7? Well, no, that won't work. 1 times 1 is the only thing we have. And then you would do 2. Well, 2 times 1 is 2. That doesn't add to give us 7, so 2 is not going to work. 3, once again, you only have 3 and 1. That would add to 4, so that's out. Factors of 4, you have 4 and 1 or 2 and 2. Neither of those add to 7, so that's out. We go to 5. 5 and 1 would add to 6, so that one doesn't work. 6x squared, we have 2 times 3 would add to 5, but 6x and 1x would work, because that would add to give you 7x. So it appears that when k is equal to 6, that would work. Okay, we're making some progress here. What about if it was 7x squared? Can you multiply to get 7 and add to get 7 also? Nope, that won't work. What about 8? We have 8 times 1, which would be too much, and then 4 times 2 would be 6, so 8 doesn't appear to work. 9, factors of 9 would be 3 and 3, and 9 and 1, those don't add to 7. 10, we have factors of 1 and 10, and 2 and 5, so 2x and 5x would add to 7x, so that appears that that would work also. All right, we're about halfway through now. Let's see if we keep going. 11. Factors of 11 are 11 and 1, so that doesn't add to 7. Factors of 12, we have 1 and 12, too much. 2 and 6, a little bit too much. But then we do have 3 and 4, which do add to 7, so it appears that 12 would also work. So we have 4 numbers total. If we go to 13, 13 would be 1 and 13, that doesn't work. 14, you have 14 and 1, 2 and 7, that's not going to work. 15, you have 3 and 5, that's not going to work. 16, 4 and 4 would be our smallest, and that gets us to 8, so that's still too big. So I think we're getting to be too big on all these. 17 would be 1 and 17, that's out. 18, we have 6 and 3, that's our smallest one, and that doesn't work because that's 9. 19 is 19 and 1, that won't work. 20, we have 4 and 5, that would be our smallest, and that adds to 9. So it looks like we have our 4 factors or our 4 numbers of k that would make that work. Now that's not the answer because it wants to know what the probability is, but there were 21 numbers and only 4 of them are going to work. So that would be approximately 19.05%. That would be the probability that if one of those numbers were picked at random, that it would actually be factorable. Question 75. Your teacher has offered your class extra credit. She has created 2 spinners shown at the right. Your class gets to spin only one of the spinners. The number that the spinner lands on is the number of extra credit points each member of the class will get. Study both spinners carefully. Assume that each spinner is divided into equal portions. Which spinner do you think the class should choose to spin, and why? So what we can do to kind of get a better idea of what we should pick, we can find the expected value for each spinner. So these appear to be broken into 4s. I'm going to go ahead and write this out, but it would be 0 times 1/4, and then plus 0 times 1/4. Obviously these are all zeros, but just kind of gives us an idea that each of them are being used, and then 20 times 1/4. So when you add that up, you get 5 is what you would be expected to get over many, many spins on each spin. Now, it is already looking better that the second spinner, we really don't even need to do the second one because your lowest that you can get is already 5 without any zeros. So the second spinner also, if you want points, no matter what, you would pick the second spinner also. But we'll go ahead and do it. So if we do half, we can take 10 times a half plus 5 times 1/2. So that's going to be 5 plus 2.5, so 7.5. So the second spinner is definitely going to be the better spinner in terms of the expected value. Part B, what if the spot what if the spot labeled 20 were changed to 100? Would that make any difference? I'm thinking it might. So if this is 100, then we go to part B, and we basically, we're going to take this whole thing and redo it, but what we're going to do is change the 20 to 100, and let's see what happens. So plus 100 times 1/4. Well, 1/4 of 100 is 25. Makes a huge difference as to what's going on now. So if we change it, would it make any difference? And yeah, absolutely. And then, once again, spinner 2 is going to guarantee you some extra credit points. Spinner 1's not, but spinner 1 on this scenario will give you a higher expected value. And so that's what I said for part B then. Question 76. If the rectangles below have the same area, find x. Is there more than one answer? All right, if they have the same area, so we know that the square has length of 2x, so the area of that would be 2x times 2x, which would be 4x squared. And then the area of this one is going to be x plus 10 times 2x minus 3. And you can go ahead and multiply. You can use your distributive property. You can use your generic rectangle. Either way, you're going to get 2x squared minus 3x plus 20x minus 30, or an area of 2x squared plus 17x minus 30. So if the areas are going to be the same, then we can set this equal to 4x squared. And then we can take that and we can solve for x. And you have, once again, different ways you can go about doing that. I'm going to set it equal to 0. This will give me, actually, I'm going to subtract. I'm going to go ahead and subtract the 2x squared, the 17, and I'm going to add the 30. So that would actually give me 2x squared, just to keep my x squared coefficient positive, minus 17x plus 30 is equal to 0. And then we can solve that. We can solve that equation. We can try to factor it. We can do the quadratic formula, whatever you prefer on that. I think we can factor it. So let's see here. We have 2x and an x. So this should be correct. That'll give me negative 12x minus 5x is 7x. And once again, use the generic rectangle if you need to, whatever works. 2x minus 5 equals 0. So x is equal to 5/2, or x minus 6 is equal to 0. So x is equal to 6. So if the rectangles below have the same area, find x. Is there more than one answer? Yes, it appears that there's more than one answer. We do need to kind of verify because we're talking about lengths here. So if I plug in 6, this would make this 12. So that would make sense. You could have a 12 by 12 square. If you plug in 2.5, then that would make the length 5. Once again, you could have a 5 by 5 square. So no issues there, but we need to check the other one as well. If you plug in 6, this would give you 16. If you plug in 6 here, 12 minus 3 is 9. So those are both positive units in terms of the distance. If I plug in 2.5, this would be 12.5. And if I plug in 2.5 here, it'd be 5 minus 3, which is 2. So it still works. But you do want to make sure, just because you got x equals two positive numbers or even negative, doesn't even matter. You need to check, if you're talking about distances, to make sure that both of those answers are solutions. So we did get two solutions. We got x equals 5/2 or 2.5. Or if you have x equals 6, then that would work also. And you can plug those in and check that the areas are the same. All right, question 77, multiple choice. A cable 100 feet long is attached 70 feet up the side of the building. If it is pulled taut, there is no slack, and staked to the ground as far away from the building as possible. Approximately what angle does the cable make with the ground? All right, let's get a diagram here. So the cable is 100 feet long. It's attached 70 feet up the side of the building. So here's my building. About 70 feet. The cable is attached. We have no slack. It's staked to the ground far away from the building as possible. All right. And so this is 70 feet. The cable itself is 100 feet. And we want to know what the approximate angle is that the cable makes with the ground. So that'll be right there. So it looks like we would use our trig ratios. In this case, we're going to use sine, because we have the opposite side at 70 and the hypotenuse at 100, and we're looking for the angle, so therefore we are going to have to use the inverse of sine. And then if you plug the inverse of sine in your calculator, and you have 70 over 100, you will get an approximate answer for theta to be 44.4 degrees, and those go to two places, so I'll go one more place, 44.43 degrees, and that appears like answer B would be the correct one.